Hey friends, welcome back and namaste. Last time we went to great lengths to try to start engaging with convergence and the idea of convergence. And in that, we relied on this diagram wherein we discovered that this angle is the same as the latitude. And we have a right angle here. And obviously we have latitude here. And 90 minus the latitude here. And this, of course, is our delta lambda. We have delta lambda here. And then this angle up here where C is, this is our convergence. And then we use that along with the definitions of the lengths of the sides to derive an exact formula for the for convergence. We also talked about so back when ships were requiring a lot of hand calculations for their navigation, and when the PLSS system was being implemented, convergence had to be calculated and reported regularly so that the courses they were taking could be adjusted and they could come up with the actual lines that they were trying to report or that they were trying to navigate. I could probably write what we're working on. So working with convergence. Okay, squeeze it in there. So what we derived last time was the exact formula for, as I just said, the exact formula for convergence based on using that chord between A and B and then setting two formulae equal, solving for C, and we came up with this not too bad of a formula. We got C for convergence equals 2 times the arc sine of the sine of psi, or latitude, times the sine of the change in longitude, or delta lambda, over 2, which came from that chord definition, right? And we also talked about how for the day and age that a lot of our records were created, a lot of plats we look at, or historical navigation charts. This was not a practical formula to use to calculate convergence. Working out in the field, they didn't have, or on a ship, they didn't have calculators. At best, on a ship, they might have had an abacus, or later on maybe a slide rule and some sine tables. But then the arc sine of a product of sines was not. It's not something that we could readily expect could be done on a regular basis to calculate the convergence every time they needed to correct an angle so they don't, start spiraling the North Pole. Of course, in this day and age of Excel and, advanced calculators, computing, coding, this would be no problem. But it's not how it was done historically, and most times we need to reproduce results as they were done originally. So what we need is to come up with, we need to understand an approximate method that would have been used historically. And again, I'll say like last time, there are not a lot, but there's a few different approximations that have been used to derive results, and they're similar enough that the difference can be considered negligible. But what we're going to do is we're going to build toward what BLM recommends using for convergence, since much of what we do is dependent on what was done during the PLSS system, and that's the system that BLM uses, which is an ancestor of GLO, right? Or I guess GLO is the ancestor of BLM. So let's come up with that. And since I want to leave my diagram here, I'm just going to erase all this. So, I don't know where that came from. Convergence approximation. Now, how we're going to motivate this, and I'm probably going to zoom in so it's easier to write. We have an arc here, the arc from A to B. And if you think about it, that particular arc that I just drew in red is actually along the parallel. So that is one arc. Another arc that we could consider is the arc, the Great Circle arc. And I'm going to zoom in so we can see that a little bit better. So the red arc lies in the parallel of the, or I'm sorry, in the plane of the latitude. Remember, all of these arcs are intersections of planes and the sphere, or ellipsoid eventually. And you would be, I should probably make that an appropriate color. You would be well served by thinking of these arcs that way. So the other arc we considered is the Great Circle arc that is subtended by two radii coming out from the center of the Earth. So that's another one. I guess that green arc doesn't really look right, does it? So I guess the green arc would be more like here. And there's one more arc that we can consider, right? There's an arc that lies in the plane of our convergent angle, or our angle of our convergency. So if I were to consider the plane that is tangent to the sphere and is defined by points T, A, and B, that is another arc. I can consider the arc in that plane. And I guess I'll use blue for this one. So if I were to consider this line, and you can't see that very well, can you? Maybe if I made it thicker. So that line and that line going all the way to T, right? So those two lines lie in the same plane. And we can consider the arc there. Now these are three different arcs, and that's pretty fat, but we have make my line super thick here. So we have the arc from A to B that lies along the Great Circle. We have in red the arc from A to B that lies on the plane of the latitude, or I'll call it latitudinal plane. And so this is on the latitudinal plane. That should be an I. And a third one, which is arc A, B, that lies on, what should I call that? I'll call that the plane of convergence. I don't know if it has an actual name, but and what we're most interested in are these two. Now, those two arcs are not exactly equal. There's no reason to think they'd be exactly equal. There might be a few lengths of TA or TB that might allow for those arcs to be super equal, to be completely equal, but in general, they're not equal. But they're so close. If you think about it, they're both greater than the great circle distance. So they're going to be closer to each other than either would be of the great circle distance, arc distance. So what would happen if we just set our plane of convergency arc equal to our latitudinal plane arc? I'll put for approximation. It turns out they're so similar in length that we can just neglect the difference. And I've actually compared them in Excel for different latitudes and different delta lambdas, and they really are, a traverse would have to be so long as to be unrealistic in order to even notice the difference. So we're going to set those two arcs equal to each other. So just to, if you look at the diagram, that's why everything's so fat, because I need to make this 100% zoom. So arc AB lies with the plane that contains T points T, A, and B in the diagram. And the red one, the arc AB, for on the plane of the latitude is equal to DAB. Or not equal to, but lies in the plane of DAB. It's a D. A, B. So how does that help us? Well, we know how to find the arc length, right? Given an interior angle and a radius. So for the first one, arc AB, that lies in the plane of T points T, A, and B, that would be equal to the radius that we're concerned with, which is R times the cotangent of psi. And remember, the image uses phi, but we're using psi. R cotangent psi, and that would be, so that's the length of our radius, and we would multiply that by c in radians, right? So that's pretty simple. We've done that 100,000 times. And then the other arc, AB, lying in the latitudinal plane would be equal to the R cos psi or the radius of the latitude that we've looked at since day one, times delta lambda. So that's just the regular old parallel of radius of a parallel of latitude that we've been using. So now what we're doing is we're going to, I'm going to move it up because we don't need the image anymore. We're going to set those equal, even though as we discussed, they're not really equal, but they're close enough that we can ignore the difference. So we have arc AB equals arc AB of the two different forms. Really, they're approximately equal I might as well just do that. Approximately equal, but going forward they'll be equal. And we have the first one, r times the cotangent of psi times, make sure my notation is consistent, times c equals this one, r times the cosine of psi times delta lambda. Now we just solve for c, which is pretty simple. We just divide both sides by the r cotangent psi, so c equals r cos psi delta lambda over r times the cotangent of psi, right? And of course the r's cancel out, they're just numbers. And we're left with c equals the cosine of psi delta lambda over the cotangent of psi. And we can simplify this even further. So the cotangent of an angle, so the cotangent of some angle, say theta, is equal to the cosine of theta over the sine of theta. So we can actually reduce this part a little bit. Using that definition, we end up with delta lambda times the sine of psi. And that is much simpler. That would require field crews to just use tables and some basic calculations to come up with the convergence angle. So this one is a form that you'll see quite a bit, a form of the convergence angle, and it's an approximation. BLM takes that a little bit further and uses an equivalent approximation. So we're going to expand on that a little bit. So that's a common one. I'll scoot this over. All right. This is common. But the BLM version is also common. So BLM expands on that a bit. So they do use this that we just derived. So they start with c equals delta lambda sine psi. And then they just kind of change the form of their representation of the distance along the parallel using notation we've been using. So arc AB equals, where am I here? M lambda, which is just the distance along a parallel between longitudes like we've been using. And let's just note that, again, just getting the arc length in the plane of a parallel, that's equal to r cos psi delta lambda. And that's just the arc length along a parallel that we've done since day one. So then using substitution, so we say delta lambda, we're going to solve for delta lambda here. And we get delta lambda equals m lambda, or the distance along a parallel between longitudes, over r cos psi. There we go. And we take that and we substitute into the approximation that we just derived. And if we do that, we get C equals m lambda over r cos psi times the sine of psi, which comes out to be, scoot this up just a bit, C equals m lambda times the tan of psi over r. And that tangent just comes from the definition of tangent. So tan equals sine over cosine, which is what we have, sine and cosine. And it works out. And this is what we're going to use for convergence in a spherical model. And that is, in fact, what BLM uses and recommends. So this is what we're going to use for convergence of meridians on a spherical model. And that's what we'll use in homework too. For assignment 2, we'll use the spherical model. Okay, so now we have an apt approximation. If you plug in value, if you make an Excel spreadsheet with convergence, and I might do this at some point if there's time, but with different latitudes, longitudes, and the two different equations, and you compare the results, you'll find that their difference is so negligible to the exact as we don't even need to worry about the exact. And those approximations are performed quite a bit in geodesy, map projections, any environment in which we have to move back and forth between Euclidean and non-Euclidean environments. So spheres and planes, or ellipsoids and planes. We do a lot of approximations because some of the math is extremely difficult and impractical, and a lot of the math is, in fact, impossible. It's unsolvable. So we make approximations within our practical margin of error. So highlight that one in your notes and keep using that one. I lost my pen. There we go. I found it. This guy here is what we're going to be using for convergence. We just had to go through some steps to derive it. All right, why don't we do an example? We're going to look at a traverse. And before we look at a traverse, I'm going to bring in another diagram to just kind of talk about it a little bit. All right. There we go. So here we have a traverse, and we have our grid north, and then our computed azimuth at the end. And this says convergence is a systematic error because it follows a defined pattern that can be mathematically quantified. So since this is a systematic error, it can be calculated and removed before we perform any kind of an adjustment, right? Recall that adjustments, whether it's a compass rule adjustment or it is a least squares adjustment, Crandall rule, there's others, but Adjustments are designed and effective at removing random errors from traverse calculations. In order for the adjustment to work properly, any kind of an adjustment, we have to remove blunders and systematic errors. Those will contaminate the results of a good adjustment. And convergence is, in fact, a systematic error. It's not a random error. So we need to remove it before we perform an adjustment. How do we do that? So the disposition of the systematic error caused by convergence is a larger issue. It is clear that convergence is not random and should not be allocated by the compass rule or by the use of a least squares adjustment or any other adjustment for that matter. And let's see, let me bigify that. I'm gonna bigify that so I can draw on it. There we go. Alrighty, so here we are. We're going to start at this. I've been using points A and B. I'm just going to keep doing it. So we start our traverse at point A and calculate a known azimuth in the beginning. So this is our beginning azimuth. And as we move along, we calculate angles right, add them to our azimuth, mod out 360 when we need to, and we end up over here at point B. And I'm just showing this image mostly because I got to talk about convergence being a systematic error and needing to be removed before we contaminate the computed results in an adjustment. And when we get over here to B, you can see we've accumulated some convergence that we're going to have to account for. And then our computed azimuth would then be would be this right here. So it would be our total azimuth that we computed, closing azimuth, minus the convergence. And remember, here, convergence is, what is it? The grid north. This is grid north. And this is geodetic north. So geodetic north is west of grid north. So let me look at my notes. What did I say that was? Let's see. We said when geodetic north, or when grid north is east of geodetic north, then we have a positive. So convergence is positive. And so then we would subtract it, right? So let's see. So our computed azimuth if we look at the diagram, how this works, it would be our closing azimuth, or what we calculate with all our angles right based on the starting azimuth. So it'd be the closing azimuth minus convergence. And that way we wouldn't need to calculate that convergence at every control point that we occupy. We just calculate it at the end. All right. I think we should do an example. I promised an example and then I got into this, but let's do an example. So let's see, I'm going to move that off. And let me see what I have for an example. Change colors here. Something more pleasant than red. Example. Given a traverse has a total departure and if you think about what departure is, that's our m lambda, right? That's our horizontal components of our traverse. So has a total departure of 10,362.78 international feet. Aha. Take notice of the units, okay? Because we're going to be working with different kinds of units here. And the average latitude so the average of the latitude of point A and point B is what we're about to write down here. But when we are calculating convergence, we calculate convergence based on the average latitude between 2 points. That is, if the points don't lie on the same latitude. Obviously, if they lie on the same latitude, the average is going to be the same as the latitude on which they lie. But if 2 points lie on different latitudes, we just average the latitude and use that latitude for our convergence calculation. So the average latitude in these is psi equals 31 degrees, 48 minutes, and 02 seconds north. There were 8 angles measured. The actual angular closure error was 0 degrees, 01 minutes, and 32 seconds. So we do this loop, we run our east-west traverse, and we come up with an angle closure of 1 minute, 32 seconds. And we know we performed calculations in planar coordinates, so there must have been some of this that's convergence. So the question is, once we account for convergence, oh wait, before we get to that, I haven't given our standard deviation yet. So we performed 8 angles, and I'll say we expect a standard deviation, sigma, of plus or minus 15 seconds per angle. The question is, once we account for convergence, does our traverse fall within the expected error? So a couple of things. We have all this data. We have measurements. We have standard deviations. And we need to figure out 2 things. 3 really. 1, what is our convergence? 2, what is our angle, or what is our misclosure once we've accounted for convergence? And then 3, does it fall within the expected error? So we're going to have to figure out what the expected error is first. Let's see, I need to move that up just a wee. There we go. So I'm going to have to keep track of these values. So the first thing is, I'm going to change colors here. Solution. One. What is our expected error? I'll put total. Well, our expected error, I'm going to move this up even more. No, I can't. Okay, our expected error, if you remember way back to plane surveying, computations, and platting, our expected total error, so I'm going to say sigma sub t for sigma total, or total standard deviation, would be our sigma 15 seconds per angle times the square root of the number of observations, where n equals 8 and sigma equals plus or minus 15 seconds. And I'm going to have to move this up. I hope you wrote this down so you can refer to it. I'm going to have to look back at my notes. So that's easy. We've been doing that for a while. So our sigma total, or our total expected error, is equal to plus or minus 15 seconds times the square root of 8. And that gives us 42.4 seconds expected error. And that's a plus or minus. So once we remove the convergence from our, and if you'll remember, our angular closure, AC, our angular closure was, what was it, 1 minute? So our actual angular closure falls well outside this margin of error, doesn't it? It's what, more than double, almost triple, more than triple, or I don't know, 60 base math, who can do it? But it's more. We would have, if we don't account for convergence, we just failed our traverse. And if we don't know that convergence can contribute systematic error and remove it prior to a traverse or prior to an adjustment, we may send field crews out to check errors in angles that aren't there. So we're wasting money, right? It's also not very interesting. So the second thing is, what is convergence? Forgetting question marks. So this is where we use our fun little approximation that we came up with. So C equals, what was it? M lambda, or our distance along the parallel, or our departure, our total departure. I'm going to write that so it doesn't look like two variables together. Looks like they're supposed to be multiplied. So C equals M sub lambda times the tangent of our average latitude over R. So what does that equal to? Well, M lambda was 10,362.78 feet, int feet, times the tangent of our average latitude, which was 31 degrees. And of course, we would convert all of these angles into radians, 48 minutes and 2 seconds. And I'm going to purposely make a mistake on this and see if you catch it. So that's over R, which is our typical 6,371,000 meters, right? So, who caught my mistake? Did you catch my mistake? If I were to go with this set of numbers for my calculations, I would be way off, wouldn't I? Because I have international feet on the top and I have meters on the bottom. So I need to either convert the international feet to meters or the meters to international feet. And since my data was given in international feet, I'm going to convert 6,371,000 to international feet by dividing by 0. So meters divided by 0.3048 equals int feet. We went over that at the beginning of the term, but I'll just reiterate it. It's been a little bit. So there you go. And when I do that, I get 20,902,231.971 feet. Int feet, international feet. Okay, so now my units are all good. Of course, I would convert to radians before I do math, but I'm not going to do that here. And once I perform that calculation, I get convergence, convert it back into DMS for reporting, remember, equals 0 degrees, 0.1 minutes, and 0.3.4 seconds. Now I get to remove that from my total angular error. So the actual error equals my measured error. Let's see, I guess I'll use M error, our measured error, minus our convergence, and when I, which is right here, so that would be what? My experience closure was 1 minute 32 seconds minus 1 minute 0.3.4 seconds, and altogether I end up with about 29 seconds actual error, actual angular error. And if you remember, my sigma total was equal to 42.4 seconds. Aha! So now my actual error has fallen within my expected error. So 29 seconds is less than 42.4 seconds, and check. I'm good now. So if we didn't know how to account for convergence, we would be failing a traverse unnecessarily. We'd be reporting having failed a traverse that we actually succeeded. So convergence makes a difference, and that was only 10,000 feet. That's 2 miles. So in just 2 miles, and that sounds like a lot, but if you consider cadastral surveying, oftentimes I'm running lines of 3 miles, 4 miles. Building highways, they have long straightaways over 2 miles. Certainly those exist, especially down in the deserts and in the flatter areas. It's really important that we account for convergence, apply it to our azimuths, and get good results within expected error. And then know how to gauge against expected error, right? So also, if you remember last time, I made this chart, or this sort of pseudo map of moving along a parallel. And I had a starting point and ending point. This will look familiar as I build it. And I had all of these. I'm not going to be super careful anymore. I had all of these grid norths. And then I had these geodetic norths, whose angle was changing, decreasing as we got toward the prime meridian. If you've already drawn this, you don't need to draw it again. I'm just redrawing the same thing. So prime, or I keep saying prime, it's the central meridian. And then our convergence switches directions, right? Now we're, I don't want that to be a straight line. And so on. We did that. Okay. From this, we get a couple of observations. One, convergence, let's see, decreases. I'm going to say the magnitude or absolute value of convergence decreases as we approach the central meridian. Two, and I think I'm going to do it up above. So over here we have negative convergence until we get, so negative convergence, negative convergence, negative convergence, negative convergence, and here, right at the prime meridian, convergence equals 0, and then we have positive convergence, positive convergence, positive convergence. Okay, so convergence is negative when west of the prime meridian, and it's positive when east of the prime meridian. And we could put that differently, like I put last time, that our, when our grid north is west of our geodetic north, then convergence is negative, and when geodetic north is west of grid north, we have positive convergence. That's just another way of saying the same thing. And it's 0 when at the prime meridian. So just a few notes to help out with the concept image of convergence. Okay. So now we have, I'm just going to wrap up here in a nutshell. So for spherical model of convergence, we have C equals m lambda times the tangent of psi over r. And we also have, since we're about to move into the ellipsoid, exciting stuff, then things get really fun. Convergence on the ellipsoidal model is a little different. It's anatomically the same, but there's some complications for the non-uniform radius of an ellipsoid. So I'm just going to throw that out here, and we will revisit at some point in the future. So that equals, we start out the same, m lambda times the tangent of phi. So in an ellipsoidal model, we use phi instead of psi. So ellipsoid latitude is noted by t, or phi. So far the same. But then we multiply that by 1 minus, we have to account for the flattening, from a sphere to an ellipsoid, and this is how we do it. 1 minus what's called the eccentricity squared. And we're going to look at these numbers, so I'm just kind of giving you an introduction, times the sine of phi, or the latitude, the ellipsoidal latitude. And it's the square root of that, everything in the brackets. All of that, now over here we were over r, here we're over a, which is the semi-major axis of the ellipsoid. So between that flattening component here, and the fact that we're using the semi-major axis, that is how we account for that non-uniform radius. So next time, we're going to start looking at the ellipsoidal Earth model. Fun stuff. And I'm going to leave it with that. We spent 2 days on convergence in a spherical environment, and that's more time than I plan to spend on it, but I think it's really important to drive these concept images home so you're more comfortable when you're drawing out your sketches, figuring out what diagrams to use. Be sure to play with that that first diagram of convergence I used with the wedge, and go through some of those derivations. They'll really help. So with that, I know I say with that a lot, but we're going to call this one done. And this one was a little lighter than last time, but gave you some good ways of working through the information. Anyway, have yourself a great day, and I will talk to you later.